We're going to do a problem dealing with some of the concepts we dealt with in lecture 2, which is number average degree of polymerization, or number averaged molecular weight, which is related to number average degree of polymerization, and number averaged or weight average molecular mass. So we did a couple of problems of those in the notes with some small number of polymers, but I wanted to do a little bit more of a realistic problem you might encounter in real life, in industry, or in academia. Because generally when you produce polymers, you produce a lot of polymers. If you get, typically you might be given a sheet, a mathematic or an Excel sheet, something like this. So here, this is just a list of 1 mole. Basically, it's a mole of polymer for each molecular mass. So this is basically your M sub i's, and each of these polymers corresponds to 1 mole of basically polymers. So this 62,000 is 62,000 molecular weight, M sub I, effectively in your equation, in grams per mole. So we're going to take this list. We're going to figure out from this distribution of polymers, from a long list, how it looks like, how the distribution looks like, and we're going to calculate M sub n, M sub w, PDI, DPN, all that good stuff. So let's go ahead and I'm going to copy this path. I'm going to open up Mathematica, and we'll go ahead and get started here. And we'll actually pull up the notes on the side as well. So let's go ahead, excuse me, right here, I'll pull up the notes. Let's pull up Mathematica right here, and we'll go ahead and get started. So I'm going to import my raw data, import, I'm going to do data, and you see there's lots of parentheses here, so I'm going to flatten this, flatten my data. And these are the polymers I'm working with here. So I'm going to suppress this output. If I want to kind of look at the distribution, let's look at the mean of our data just for, just to be interesting. Standard deviation, so 500,000. Okay. Kind of see what we're working with. We can also just look at a histogram of our data. Nice. Looks pretty normally distributed. Again, depending on your application, this width might bother you, but let's calculate the number average molecular weight and the weight average molecular weight. So number average molecular weight, we just said previously that for each element in our data sheet, so our data, so if I pull out the first, this is just the M sub I, and we know that the number of polymer chains we have there is 1 mole, so 1 mole or 6.02 times 10 to the 23rd, polymer chains, but we could just kind of dimensionalize, or, we could just zero out by the number of moles, for example. It's basically equivalent. But anyways, so all we have to do now is to calculate the number average molecular weight, we need to sum all of those values. So I have a function in Mathematica, since we know each of them are equally just one number or 1 mole of polymers, all I have to do is look up and use this function called total. Total is equivalent to basically a sum. So it's just the total, the sum of the elements in your list. So it's just going to be A plus B plus C. So that will be equivalently what we're going to do here. So M sub n is going to be equal to total. I'm going to capitalize it. Total of our data, and I'm going to divide by the length of our data. Length is just the number of the list, so it's the number of basically moles of our polymer chain. So there, that's our M sub n. To calculate our M sub w, it's going to be a very similar looking equation, except we're going to have to do a little kind of a trick here. So let me scroll down, pull Mathematica back up. So there's our, that's another sheet, excuse me. Let's pull up Mathematica. To get M sub w, we're going to have to do something a little bit different. So what we need to do is, first, we need to do, I'm going to take out our data. So we need to square this value now first. So I am going to do a table. So I'm going to create a table of this. I'm going to go from, I can actually do this a little bit. I'll show you a nice, I like to do it rigorously. So I'm squaring my data first, making that list. I'm going to do a total now, because again, we still have to sum. Still, M sub I is no big deal. So that's my numerator. My denominator is just going to be the exact same as my N sub n. That's why it's nice to kind of calculate it here. And this would be my M sub w. Sanity check, M sub w always have to be greater than or equal to M sub n, and that works. I could also have done this a little bit nicer if I just did total R data squared. Let's see if I get the divided by total data. Yeah, same value. Good sanity check as well. So my PDI is just going to be M sub W or M sub N. That's a pretty nice PDI. Remember, if you're at 1 or 2, 1.5 to 2 is normal for most polymers. It could vary, most realistically 1.005. So this is a really amazing polymer chemist. 1 would be obviously perfect, and that's very, very, very difficult to achieve experimentally. To calculate my DPN, I would just divide my M sub N by my M sub R, and whatever the mass of your repeat unit is. So if it's polystyrene, or if it's polyethylene, or if it's polyethylene oxide, you just divide out by there, and you get the degree of polymerization of your polymer chain. So yeah, that's quickly how to do and how to calculate your number average and weight average molecular weight. So good luck on your problem set. If there's any issues pop up, let me know, and we'll make some more videos. All right, thanks. Bye.